Hello, everyone. So my name is Samwel Sekwao. This is from INQ. This is a video recording going through the answers of my challenge problem. The title of my challenge problem is Simulating Fluid Dynamics on a Quantum Computer. In this challenge problem, we're going to apply the quantum lattice-Boltzmann method to a simple implementation of the quantum lattice-Boltzmann method on the one-dimensional adventure diffusion equation. Now I'm gonna skip over the lattice-Boltzmann method background section. So the quantum implementation of LBM involves 4 steps: initialization step, the collision step, the streaming step, and the addition step. So, and then I created questions based on each one of these steps. So let's get through the questions. So the first step is initialization. So this encodes the distribution in a quantum state. This can be done by using 2 registers, Q for the spatial dimension and D for encoding the particle distribution functions. Now, for a lattice of M cells and Q macroscopic velocities, the first question is how many qubits in the Q register are needed to encode the initial state? The answer here is log base 2 of M, where M is the number of cells. Basically, M is just the length of the vector which encodes the initial state. Part B is how many qubits in the register D are needed to encode the distribution functions. If you have Q macroscopic velocities, the number of qubits in the D register is sale of the log Q to base 2. I hope those two were simple enough, and I hope most of you figured that out. Now, part C, suppose M is equal to 64 and Q is equal to 3. And we have an initial distribution which is 0 everywhere, except at the point X source is at X source, which is at the point 32, where the distribution is 1. Using Qiskit, write a function which initializes this initial state. So I created that function. I'm going to call it initialize 0 for reasons which we'll see a little bit later. It takes in the density, which is the initial density, and the number of velocity, which is Q, number of macroscopic velocity. So you can see here, walk through the function, takes in the density, number of velocity vectors, and returning a quantum state, which is initialize the density. So going through this, we're going to need 2 registers, as you see in the code. Register QX for the state, and then QD for the microscopic distributions. One thing to note, the density has to be normalized so that you can use Qiskit to initialize. So I have that in this line right here. And then the rest is to initialize the density in the first NQ qubits. For our example, you can see this M is equal to 64, Q is equal to 3, and this is the initial distribution. And then using that function, I can initialize this state. And here is a quantum circuit, which initializes that circuit, as you can see here. Okay. Yes. I hope that was, I hope everybody figured out how to do that. Now, the second stage of this QLBM method is the collision stage. Now, for a uniform velocity field, which is what we're interested in this example, the collision step amounts to preparing the state K, which is given by this equation here. Now, where ND is the number of qubits in the D register, and the constants Ki are given by equation 6. I already defined equation 6 if we go up here. As you can see here, this equation gives the constants Ki. So this amounts, collision step in this case amounts to just preparing this state preparation on the D register, this state here. For this, we need the weight coefficients. So I've given an array of weight coefficients here for the macroscopic distributions, 2/3 for F0, 1/6 for F1 and F2, and then the corresponding speeds, 0, 1, and -1. 0 means the particle stays there, 1 to the right, and -1 to the left. Adventure speed 0.2 is given, and we're assuming the speed of sound is 1 in this case. And then based on that, you know, we can find this function which initially implements the collision step, which is given in this cell number 4 here. This is the initialize step. So this function initializes a quantum circuit, initial state, and applies the collision operator. Okay, the inputs are density, initial density, and the k vectors, which are found from equation 6. Note that the condition to use this function is the inputs must be normalized. Okay, let's walk through the code. M is the number of cells, which is just the length of the density. NQ, as we've discussed above, and ND are calculated, and the two registers, QX for the state and QD for the particle distribution. And then the quantum circuit is initialized, and then we initialize the density in the first NQ qubits, and then initialize the K vectors from in the D register, and that returns the quantum circuit. So I have the example that which is asked in the part 2. We have the initial state, which is defined above. You can calculate the norm here and just normalize the state, and then the constants are given: adventure speed, speed of sound, and the weights. And then this is a particle of speeds as described above. And then this calculates the weight vectors by using equation 6. And this is the normalization vector, normalization constant for the weight vectors. And this is and then we normalize the k vectors. Now, this is crucial. To use Qiskit initialize, the length of the vector must be a positive power of 2. In this case, we have 3 particle directions. I just append this with 0, paired with 0, so that the number of ki is 4, which is a power of 2. And then after that, once we have the initial state and the k vectors, we just get a quantum circuit by using the function described above. And in here is the circuit. As you can see, the first 6 qubits I initialize the states, and the last 2 qubits are initializing the particle distributions, as you can see here. I hope everybody figured out the question. Let us continue. Part 3 is a little bit involved. This is a streaming stage. So this is the distribution function propagating the direction corresponding to the velocities in this step. As we discussed before, if we have velocity vector 0, 1, and -1, which means stay where you are, move to the right or move to the left for the functions, for the distributions f0, f1, f2, and f2 respectively, and periodic boundary conditions. So streaming can be achieved by using shift operators. The shift operator will shift f1 to the right and f2 to the left. Obviously, there's no shift operator for f0. And this can be implemented on the quantum circuit by, these R and L operators are applied on the Q register, okay? And then you can see here, similarly what they do, these operators, the right shift and the left shift operators. Now, part A of this question is, what is the product RL? Obviously, the product RL should be identity, and you can check for yourself, as I added a check there. I hope that was simple enough for everyone. Part B, use Qiskit, write a function that implements the operators R and F for n cubic states I. And then I give a hint here. What does the circuit look like for 2 and 3 qubits? So the right, and left operators, actually, I've implemented them for you. They're going to be shown in part C. And also, if you want to see more details of the implementation of the shift operators, they can be found in reference number 3. So basically, I've answered part B. The implementation is included in part C. Now on to part C. After the collision, R and L are applied to the right distribution. Okay, and these operators must be applied conditional on the direction register. So for this case, if we choose F0, F1, and F2 being encoded by the state 0, 0, 1, 0, 0, 1, and 1, 0, respectively in the register D. So using Qiskit, write a function that applies the streaming step after the collision step. So for an answer, like I said, we can look at the function defined below. I'm calling streaming D1. It takes in an initialized quantum circuit and applies the streaming operators left and right. The first part in the function is building the left and right operators. As you can see, I'm creating sub-quantum circuits for the two operators and applying the right controls. And then I'm making these as gates here. The right and left, they're going to become gates. And then we apply the right control. Remember, these operators must be controlled on the qubits in the D register. In our case, the number of qubits in the D register is 2. So like I said before, right is the control state for 1 is 1, 1 0. The control state for left is 0 1. Okay, so you can see here. Now, once you get the control gates, you can apply them in the quantum circuit in the right qubits by using this qubit mapping here. So you can see here, I find the mapping for both operators, and then I just apply here. Apply the right operator, right shift, and then here, the left shift operator. As an example, we already have a quantum circuit that's initialized. So I'm using this function, stream D1, with the already initialized quantum circuit. So that should do the trick. And then I'm drawing the circuit. So let's see how it looks like. As you can see, these blocks here. First, the quantum circuit has been initialized with the state and also with the direction, with the particle distribution functions. And then you can see the implementation of the right shift and the left shift and the right conditions on the D register here. So I hope everybody enjoying solving that problem. Now, the last step is the addition step. This calculates the macroscopic densities according to the equation 2 above. Now, this can be achieved by applying just R mods on the qubits in the D registers and getting the right summation, okay, which is, post-selection. So the question here is, which state on the D register will give us the desired state after one time step? So the right summation is the state of the quantum circuit where we have the 0 state in the D register. You can check by yourself when you apply Hadamard's. The 0 state will give you the right summation. But it's that's not the end of the story here. Now, when you apply Hadamard's, introduce to the factor of 1/2 squared of number of Hadamard states. So to get the right state, the final state must be multiplied by that factor, which is introduced by Hadamard's. For us, the numbers, as you can see the circuit above here, the number of qubits in the D state is 2, so it's going to be, the factor here is going to be 1/2 2, which is just 2. And the normalization constant, we also have to multiply the normalization constants for the density and the k vector to get the right final state at t is equal to 1. Okay. I also added another function here. I call it addition. This performs the addition mainly by just adding Hadamard states to the right register, to the qubits in the right register. So you can see this is the addition function here. So you can see I'm just applying Hadamards to the right qubit, to the qubits in the right register. So as you can see here, and also, so we already have a quantum circuit that's been initialized, collision applied, and streaming applied. So we take the same quantum circuit and do addition on it, as you can see here, and I'm drawing the circuit. So you can see the previous steps, and then the two Hadamards are applied to the qubits in the D register to do the addition. So that constitutes the entire process of simulating one time step for this using this quantum LBM methodology. Now we can do a lot more than this. We can simulate for more time steps. So to do that, we also need to read out the final state, and then we need a backend. So the backend I'm going to use is the state IR Qiskit IR state vector simulator. And what I did, I created a function, I'm just going to call it QLBM, which combines all the steps above, initialization, collision, streaming, and addition, and applies the right normalization constants to simulate fluid flow given a density, initial density, time steps, the weights, particle velocities, advention velocity vector, advention velocity, and the speed of light. So I can see this is the function here. I'm going to call it QLBM. So this is the initial state, the function, and then I'm just calculating some numbers that I need here, like the number of cells and the density. I also need the K vectors for the collision step. So you can see, as previously you've seen, I did this, and I also need to have the normalization for these K vectors because that is needed. And also, as before, this I need to append a 0 to have the right power of 2. The number of elements in the K vector has to be the right power of 2. And then this is the constant that I need to apply the final to multiply to the quantum state 2. And this has to do with application of the Adamats, introduces 1 over square root of 2 over nd. So I need to multiply by that to get the right addition. So for whatever, and then here's the loop doing the QLBN for each time step. So you can see I do need to record the normalization state for each normalization constant for at each time because it's, as I said, it's needed later. So the distribution has to be normalized, as you see, and the K vectors are already normalized. So this step here does the initialization, and of course, streaming on the quantum circuit, maybe add a barrier here, and then addition. Okay, the addition step was described above on the barrier, and then we get a compile circuit using QCenter transpile, and then results. We do a simulation, use backend.run, the backend is the state vector simulation, and the state vector that we need is, we can just get an array from results.get state vector, but because we need to do post selection, okay, the final state at t is equal to, at t plus 1 has to be, we get the state vector only the first m elements, because remember the state on the D register must be 0, 0. So we only care about the first m element, where m is the number of sites, the density, and then we multiply by the right normalization constants. Normalization from the original state, normalization from the K vectors, and the constants for addition constant due to the Hadamard's, and you get the state in the next time iteration. So basically, I created this function for you. Hopefully, you created a version of this on your own, something a little bit different. So this will simulate this fluid flow for however many time states you want. So the simulation part. So all of these answers for in section 5, parts A, B, C, D, they can be answered by using the quantum state, by using the quantum function, QLBM function given above. So let's set up the problem. We are given U, advention velocity, speed of light, the weights, particle velocities, and of course, our initial density. So you can see here, number of sites, and we want to simulate this up to 20 time steps, but we're recording every time step. And then you can see here, describe the initial density, and then run the algorithm. So this object here, this array here, call it, once I call this function with the density, time steps, weights, and all these other parameters, this gives me the state at all times, all the way up to t is equal to 20. And then plotting the required states at t is equal to 0, t is equal to 1, t is equal to 2, and t all the way up to t is equal to 20. As you can see, here's a plot of all the states as a function of position. So you can see it for yourself here. Yep, that's it. I hope everybody, I also added a few references here, so you can look into that. And I really hope everybody really enjoyed solving my problem. Thank you very much.